Imagine you could look back in time. Not just a few years or even a few million. Imagine you could see the universe as it was just after it was born. This isn't science fiction. It's something we can actually do. We have a photograph of the infant universe. It's a faint glow that fills the entire sky, a whisper from the very beginning of everything. This ancient light is called the cosmic microwave background, or CMB for short. It is the oldest light in the cosmos, a relic from a time when the universe was incredibly hot, incredibly dense, and just getting started. Think of it like the heat you feel from a bonfire that has just been put out. The flames are gone, but the embers still glow, radiating a gentle warmth. The CMB is like that warmth. The fiery creation of the universe is long over, but the residual heat, stretched and cooled by the expansion of space, remains. In the 1960s, two American radio astronomers, Arno Penzias and Robert Wilson, were working with a large horn-shaped antenna in New Jersey. They were trying to use it for radio astronomy and satellite communication, but they had a problem. They kept detecting a faint, persistent noise, a microwave hiss that seemed to come from everywhere in the sky. In a now famous effort, they even cleaned the antenna to remove what they described as a white dielectric material, which was, to put it plainly, pigeon droppings. But even after evicting the pigeons and scrubbing their mess, the strange hiss persisted. Meanwhile, just a short drive away at Princeton University, a team of physicists led by Robert Dicker was on the hunt for this very signal. They had theorized that if the universe began with a hot Big Bang, the residual heat from that explosion should still be detectable. The moment they spoke, both groups realized what had happened. Penzias and Wilson had found what Dicker and his team were looking for. This discovery was one of the most important in the history of science. For their accidental yet brilliant discovery, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978. They had opened a new window onto the cosmos, allowing us to listen to the universe's first cry. So NASA launched the Cosmic Background Explorer satellite, or COBE, in 1989. After years of scanning the sky, COBE produced the first ever detailed map of the infant universe. The map showed an almost perfectly uniform temperature, just as Penzias and Wilson had found. But when the scientists subtracted that uniform glow, they saw exactly what they were hoping for: tiny fluctuations, minuscule temperature differences of just 1 part in 100,000. The slightly denser, hotter spots, shown as red or yellow in the maps, represent areas where gravity had a slightly stronger pull. Over millions and billions of years, these regions pulled in more and more matter, eventually collapsing to form the first stars and galaxies. Following COBE, even more powerful satellites were launched, like NASA's WMAP and the European Space Agency's Planck mission. Each mission gave us a sharper, more detailed picture of this ancient light. When the first detailed map from the WMAP satellite was finally processed, the scientific community honestly held its breath. At first glance, everything looked perfect. The map revealed a stunningly intricate pattern of hot and cold spots, but as physicists began to dig deeper into the WMAP data, they started to notice something strange. They looked at the lowest notes of the cosmic symphony, the largest scale patterns. Specifically, they examined the quadrupole and the octupole. To their astonishment, the scientists found that they were not random at all. The axes of the quadrupole and the octupole patterns were aligned with each other to a remarkable degree. It was like putting on a new pair of glasses and seeing the world in sharp focus for the first time. This alignment was a complete shock. It was a feature that simply should not exist in a universe governed by the principles of cosmic randomness. The finding was so bizarre that at first many scientists assumed it had to be a mistake. This perplexing alignment was so challenging to our understanding of the cosmos that it was given a provocative and memorable name, the axis of evil. The name, coined by cosmologist João Maguejo, doesn't imply anything genuinely malevolent, of course. Rather, it reflects the profound and frustrating nature of the problem it poses for physics. It's evil in the sense that it threatens to undermine the cosmological principle, one of the most fundamental and cherished assumptions in modern science. This axis suggested that maybe, just maybe, we do occupy a special place in the universe. The discovery of the axis of evil sent ripples of shock and excitement through the world of cosmology. It was a direct challenge to the standard picture. The scientific community was divided, and a great debate began that continues to this day. Was this a statistical fluke, or was it a crack in the very foundations of cosmology, a signpost pointing towards a new and revolutionary understanding of the universe? The teams behind both the WMAP and Planck missions went back to the drawing board. They embarked on an exhaustive campaign of diagnostics, scrutinizing every aspect of their experiments. They re-examined the way the satellites scanned the sky, their precise orientation in space. Every line of computer code used to process the raw data was double-checked and triple-checked for hidden bugs or flawed assumptions that might have biased the final map. It was a painstaking process of cosmic detective work. The sense of unease grew when the European Space Agency's Planck satellite released its data years later. Planck was a far more sensitive and sophisticated instrument than WMAP. Many cosmologists hoped that its superior data would make the anomaly disappear. Instead, Planck confirmed the alignment. It was still there, clear as day in the new, higher-resolution maps. The axis of evil was not an illusion. After years of this rigorous cross-examination, a consensus began to emerge. The shadow, it seemed, was not in the machine. It was out there in the cosmos itself. So, if it's not an error, not a foreground, and not just a fluke, then we're left with, honestly, the most exciting and radical possibility of all. The axis of evil is real, and it's pointing us toward new physics. This is actually the conclusion that a growing minority of cosmologists are beginning to seriously consider. Some proposals suggest that the universe isn't the same in all directions, that it's anisotropic. Maybe there's a genuine physical preferred direction imprinted on the fabric of space-time itself, a remnant of some exotic event in the very first moments after the Big Bang. Other theories explore the idea that the universe has a non-trivial topology. It might be shaped not like a simple infinite sphere, but more like a donut or some other, complex, multi-connected shape. Even more exotic ideas have been put forward, collisions with other bubble universes in a larger multiverse. These are honestly mind-bending concepts, currently far beyond our ability to test directly. But the axis of evil provides a tantalizing, albeit circumstantial, piece of evidence that encourages physicists to think outside the conventional box. Let's just pause for a moment and really consider what it would mean if the axis of evil is a sign of new physics. It would force us to abandon one of the most fundamental assumptions in all of science, the cosmological principle. For centuries, our progress has been defined by removing ourselves from the center of things. The axis of evil hints that there might be a cosmic axis pointing back at us, suggesting a structure that's fundamentally different from the random, uniform cosmos we had imagined. To suggest this principle might be flawed is a radical, almost heretical idea in cosmology. The equations that describe the Big Bang and the expansion of the universe are vastly simplified by assuming isotropy. If we have to throw that assumption away, the maths becomes, honestly, monstrously complex. But science has to follow the evidence no matter how uncomfortable the destination. It's a crack in what otherwise appears to be a perfect mirror. If the crack is real, it means the reflection we've been looking at is distorted. It means our simple, elegant, and democratic universe might be an illusion, replaced by something stranger, more complex. The path forward in solving this cosmic whodunit is clear. We need more data and new ways of looking at the sky. Cosmologists around the world are already designing the next generation of experiments, like the Simons Observatory in Chile or proposed new satellites. They will focus not just on the temperature of the CMB light, but also on its polarization, the orientation of the light waves. This is a whole new dimension of information that could hold the key. Polarization data could be the ultimate tiebreaker. Beyond simply mapping the CMB, scientists are also looking for other ways to test the cosmological principle. They are creating vast, three-dimensional maps of millions of galaxies to see if their distribution shows any unexpected large-scale alignments or preferred directions. If the axis of evil is a real feature of our universe, its influence should not be confined to the CMB alone. We should start to see its subtle shadow elsewhere in the cosmos. This is the frontier of modern cosmology. So where does this leave us? We stand at a fascinating crossroads in our quest to understand the universe. The scientific community remains deeply, and healthily divided on the matter. On one side stand the pragmatists, who argue that we should not be so quick to abandon a theory that has passed every other test with flying colors. On the other side are the revolutionaries, or perhaps the hopeful explorers, who see this anomaly as something much more profound. They argue that to ignore such a clear and persistent signal would be to turn our back on a vital clue from the universe itself. The axis of evil reminds us that the universe is under no obligation to make sense to us or to conform to our neat and tidy theories. It is a humbling and exhilarating thought. We have peered back to the dawn of time itself and found a question mark written across the entire sky. The answer, whatever it may be, promises to reshape our place in the cosmos and to tell us something new about the fundamental nature of everything. The universe may indeed be hiding a secret from us, but it is a secret that we are determined to uncover. The search for answers will continue, and with each new discovery, we get one step closer to reading the full story written in the stars.